So, in this lecture, I want to take you on a journey inside a neutron star, from the surface to the center. When we talk of a neutron star, very often there is a misconception that a neutron star is just a gigantic atomic nucleus consisting of neutrons. It's just that it is 10 kilometers in size and about 1 solar mass or 1.4 solar mass. This would not be a correct thing to say. And I would like to therefore take you on a journey. Obviously, nobody has been to the center of a neutron star. So what we are going to do is to undertake a theoretical journey. And a theoretical journey is only as good as your assumptions. So I want to make clear what are the underlying assumptions and why they are very good assumptions and why you should believe very seriously what I'm going to say today. The first question that we should ask is, how does nature make neutron stars? Well, you could make neutron stars in the laboratory, but that's not the neutron stars we are talking about. We are talking about neutron stars that occur in nature. That's the question that we want to first address. Now, before I begin, I want to recall for you the fundamental theorem of Chandrasekhar that I proved for you last time. That is, if you have a gas whose total pressure is the sum of gas pressure plus radiation pressure, then we showed that if the radiation pressure divided by the total pressure is greater than 9.2%, then we said that gas will remain classical regardless of how high the density will become. In other words, the equation of state due to Boyle's and Charles will never break down. And that is the starting point of our discussion today. Now, in stars which are more massive than about 10 solar mass, whether it is 10 or 11 or 12, we don't know, but it is of the order of 10 solar mass. What calculations show is that the stellar nuclear drama, the cycle of nuclear fusion reactions, continues all the way till you form silicon, and then silicon fuses to iron, and the story ends there because the iron 56 is the most stable nucleus. Now, till that stage, matter remains non-degenerate and the safety valve remains in operation. If you remember our discussion of the origin of stellar energy, we asked this question, why doesn't the sun blow itself apart? Because it's generating so much energy anyway. So we said the sun has a safety valve, and that safety valve arises due to the fact that the gas at the center of the sun obeys classical statistics, Boyle's law. And what does that buy you? Something terribly important. In a classical gas, if I increase the temperature of the gas, the pressure of the gas will necessarily have to increase. So if I do some mischief and create more energy, the core will expand and cool and come back to the original size. That is the safety valve. I also said that if the gas is degenerate, in other words, it obeys Fermi-Dirac statistics like white dwarfs, then if I try to create energy in that by, say, some fusion reaction, let us say, to be specific, we have a carbon core which is degenerate, and I try to compress the carbon core so that carbon and carbon will fuse to form oxygen. If I did that, then what will happen is that the temperature of the core will go up because you have generated a lot of energy, but the pressure of the core will not go up because the pressure of a degenerate gas has nothing to do with temperature. And if the temperature goes up, the nuclear reaction will go even faster and even faster and even faster, and you have a bomb. Therefore, a degenerate star, if it ignites some nuclear reaction, will explode. Therefore, for this stellar drama to go on all the way from hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to neon, neon to silicon, silicon to iron, the star has to make sure that at every stage, the classical equation of state is valid. The question is, what guarantee? The guarantee is Chandrasekhar 1931, as we now understand it. Now this is because till that stage, whether you're dealing with the helium core ready to burn carbon or carbon core ready to fuse to oxygen, all the way up to silicon to iron, the radiation pressure always remains more than 9.2% of the total pressure, and therefore the gas remains classical. And therefore the safety valve remains in operation through this entire stellar drama of the curtain coming down and going up. And the reason why radiation pressure continues to remain above 9.2% is that the cooling of the core is mainly due to photons. I mean, in the nuclear reactions, you generate a lot of photons, and these photons diffuse out, so they are not instantly able to escape. Therefore, the cooling due to photons is inefficient. This is why white dwarfs, even though all the action stopped long time ago, they're still radiating. It's just the fossil heat. Now, you will recall this picture that in a massive star, more massive than about 10 or 12 solar mass, the nuclear reaction continues all the way, and if you look at the final stages of the star, what you will find is an onion-like structure where hydrogen is burning to helium, and inside that helium is burning to carbon, carbon to oxygen, to neon, oxygen, silicon, and finally silicon fuses to form iron 56. So what I'm saying is, all these stages, the gas remains classical, and therefore the safety valve remains in operation. Now something new happens when silicon fuses to iron. You remember that the Coulomb repulsive energy between the nuclei as they collide is proportional to Z1, Z2 by R. So by the time you are fusing silicon and silicon, Z1 and Z2 are very large numbers. Therefore, the Coulomb repulsive potential barrier is extremely large, and therefore you need very high temperatures to fuse these heavier elements. You need a temperature of the order of 10 to the power 10 Kelvin to fuse silicon to form iron. Now what happens is, at those temperatures of the order of 10 to the power 10 Kelvin, new physics comes in, and neutrinos are produced in very large numbers. So much so that the neutrino luminosity of the star will be 10,000 times more than the photon luminosity of the star. And since neutrinos have practically infinite mean-free path, the neutrinos very quickly will cool the star, and the iron core will suddenly become degenerate, and degeneracy will set in for the very first time in a massive star. Because of effective cooling due to neutrinos, radiation pressure finally drops below the magical value of 9.2% of the total pressure, and the iron core becomes degenerate. Therefore, an iron white dwarf forms at the center. Can we do that afterwards, please? Can we do the signing afterwards, please? Not now.
Can you just sign the paper and give to the academic office?
Yeah.
Thank you.
An iron white dwarf forms at the core of the star. A white dwarf means it's a degenerate star where gravity is balanced by the degeneracy pressure of the electrons. Now, within a few hours, the mass of this iron white dwarf will grow to the Chandrasekhar mass of 1.4 solar mass, and a dynamical collapse will occur. And it's very easy to calculate that the dynamical collapse timescale using Newton's law of gravity is a very short timescale of the order of a millisecond or less. And the end result of this dynamical collapse is the formation of a neutron star. So we have to keep this in mind before we embark on our journey. So pictorially, this is what happens in a massive star. An iron core forms at the center. And when the mass of this iron core reaches the Chandrasekhar limiting mass, which it will do very quickly because the reaction is going incredibly fast, it will collapse to form a neutron star. And the gravitational binding energy release, which is an enormous amount, 10% of the rest mass energy of this object, will blow the rest of the star apart. And you have a supernova explosion, which is schematically shown over there. The collapse of the core and a resulting shock wave propagating outwards. Finally, you have a stable neutron star and the debris of the star being blown away. So this was, of course, the conjecture way back in 1934 by Bardet and Zwicky, that supernovae represent the transition of ordinary stars into neutron stars. Very good. So now let us ask the question, what do we expect to find inside a neutron star? So what we have are three buckets. One bucket is full of protons, one bucket is full of neutrons, and one bucket is full of electrons. They are roughly same in number. And I'm going to ask you to do the following experiment using this guideline. And the guideline is nuclear equilibrium. What we say is that strong, weak, and electromagnetic forces will adjust the nuclear composition to the thermodynamically most favorable configuration. So in other words, I have three buckets in front of me. I can make any element that I want by putting my hand in and taking so many neutrons, protons, and electrons. Which is the one which is thermodynamically lowest energy? Because in equilibrium, thermodynamic demands lowest energy as being the most stable configuration. Now you may say, but look, all this only applies at the absolute zero of temperature. This neutron star is 10 to the power 10 Kelvin when it forms. The point is, very quickly, within a matter of days or a week or so, the temperature of the newly born neutron star will come down to about 100 million degrees because the neutrino luminosity will be enormous and it cools the star. So you notice I have written the word cool under inverted commas. So the point is, a star whose temperature is less than 10 to the power 9 Kelvin is an incredibly cold object. So we have discussed this many times before. What does one mean by cold and hot? You know, cold and hot, less and more, they have no meaning in physics unless you compare it with something. So when we say a matter is cold, what we mean is the characteristic energy associated with heat, which is kT, is small compared to other characteristic energies of the quantum system. So if you regard a neutron star as a giant nucleus, then you know that the energy level separation inside the nucleus is millions of electron volt. How do I know? Because gamma rays come out of the nucleus. Now, you remember 1 electron volt is 10 to the power 4 Kelvin. So, several million electron volts is several times 10 to the power 10 Kelvin. Therefore, this 10 to the power 9 Kelvin is very small compared to the excitation energy, the typical excitation energy of matter at the density of 10 to the power 14 grams per cubic centimeter, such as our atomic nuclei. But then if you say, but this is a degenerate system, the characteristic energy is really the Fermi energy, then kT is even more ridiculously small compared to Fermi energy, because the Fermi energy is of the order of 10 to the power 12 Kelvin. Therefore, a neutron star at a temperature of 100 million degrees is a far colder object than liquid helium in the laboratory. Liquid helium at milli-Kelvin temperature is a hotter body than a neutron star. Therefore, I am justified in regarding neutron star as being the lowest energy state, or in other words, neutron star as being the ground state of matter. Now, this is a very peculiar state of matter because only on the surface of the neutron star the pressure is zero, because there is nothing sitting on top of your head. Inside the neutron star, there are enormous pressure. Therefore, you have to ask the question, what is the absolute ground state of matter as a function of pressure? Let us start with zero pressure. Now, what is the absolute ground state of matter at zero pressure? In other words, given the 3 buckets of protons, neutrons, and electrons, how do I construct matter so that it is the lowest energy configuration? Now, this was an extremely challenging problem in physics, and very powerful people like Freeman Dyson worked on this for a very long time, and finally this problem was cracked. And we know the answer to this question. It took nearly 30 years, and a lot of people worrying about it, but this problem is finally understood. So this is what we believe is the absolute ground state of matter at zero pressure, and that's what we expect to find near the surface of a neutron star. Okay. First of all, when I put my hands in the proton bucket and the neutron bucket and form a nucleus, then I must remember that if I form iron 56 nuclei, the binding energy per nucleon is the largest, and in other words, it is the most stable nucleus. Therefore, the sensible thing would be to form iron 56 nuclei as opposed to any other nucleus. But then, if these iron 56 nuclei are like a gas or a liquid, then there is a lot of configurational energy, entropy associated with motion. So we would like to reduce that energy also. And the best way to do that is to tell these iron 56 nuclei stay put as a lattice. And stay put as a periodic lattice as opposed to an amorphous solid like the glass in the window over there. Because a perfectly crystalline solid has a lower energy than glass. Now that still leaves with the electrons. The electrons have spins, and these spins are oriented in random direction, and there is enormous entropy associated with the spin configuration. Therefore, you can lower the energy by asking the electrons to either point, neighboring electrons to point in the same direction or the opposite direction. You either have a ferromagnet or an anti-ferromagnet. And again, this is something that people have worked on and convinced themselves that a ferromagnetic iron 56 lattice will be the lowest form of energy. Okay? Therefore, what we expect is the outer layers of the neutron star. First of all, we would expect it to be a solid. And secondly, we would expect it to be a solid of ferromagnetic iron 56 lattice. Now, why do we expect it to be a solid? Because you can use simple considerations and calculate what would be the melting temperature of a solid and compare it with KT, which is what Lindemann did, isn't it? So he said the melting temperature would be when the amplitude of vibration of the nucleus is sort of 10% or whatever it is, 12% or 15% of the internuclear separation, a solid will melt and become a liquid. So you can use criteria like that, and you can be more sophisticated in your thinking, and people have come to the conclusion, a very firm conclusion, that the outer 1 kilometer of the neutron star will be a solid crust, but not iron 56, because our theorem in yellow over there only applies to the outermost skin of the neutron star, because that is where the pressure is 0. So I leave it as an exercise to calculate. Earlier I told you to estimate the pressure at the center of the sun and compare it with the pressure at the center of the earth. The gravitational pressure is just the weight of a unit cylinder of mass sitting above you. Calculate the pressure inside the surface of a neutron star when you have gone in 1 centimeter deep. Just 1 centimeter deep, okay? And compare that with some pressure, either the atmospheric pressure at sea level or the pressure at the center of the earth, whichever you like. You have some tremendous surprise in store for you. Now, we will see what happens, what we expect to see as you go further into the crust. But first we must ask the question, are we really sure neutron stars have a solid crust? Forget about iron 56 ferromagnetic lattice. The answer is absolutely sure. Absolutely sure. I may be wrong about iron 56, but I am absolutely sure it's a solid crust. And the reason is, we know the pulses from pulsars, which are rotating neutron stars, are absolutely stable. And we know the pulses arise because the radiation is funneled with the magnetic poles, because the particles are funneled by the magnetic poles. Now, if the surface of the neutron star is a fluid, then the magnetic field cannot be anchored to the surface. All kinds of hydromagnetic instabilities will prevent you from doing that. Therefore, we know from the stability, remarkable stability of pulses, of pulsars, that the outer layers of a neutron star must be solid. Okay? Now, these, I don't want to go into that now, but just to mention to you that these atoms, these iron atoms or whatever atoms that you're going to find on the surface of the neutron star are going to look very different from atoms that we are familiar with. Atoms we are familiar with are more or less spherical with a typical radius, which is the Bohr radius. In other words, that is the radius characteristic of quantized orbits. But our neutron star is very strongly magnetized. Its magnetic field is 10 to the power 10 Gauss. And therefore, electrons, as they move around the nuclei, they're also moving around the magnetic field. And when an electron moves around in the magnetic field, there is another radius, which is the Larmor radius, which is characteristic of, remember the Larmor frequency, EB over MC, so that can be translated to a Larmor radius. Now, it turns out that for a very strong magnetic field, the Larmor radius is much smaller than the Bohr radius. Therefore, an atom will not look spherical on a neutron star, but the atom will look like a cigar, where the characteristic size of the atom in this direction will be the Larmor radius, because the magnetic field is in this direction. Let us say this is the surface of the neutron star, and this is the Bohr radius. Therefore, the atoms on the surface of a neutron star, which is strongly magnetized, will look like needles. Therefore, this solid is a tensorial solid. It is not an isotropic solid. So we have to be very careful, and it's also a very exciting problem in solid-state physics to calculate all kinds of mechanical properties of such a solid. All right, but we won't go into this. People have worried about this, so you have spaghetti-like structures rather than billiard balls on crystal, in a crystal lattice. All right, now let us go a little further into the neutron star. What happens as you go in? The density will increase dramatically due to the gravitational pressure. So this is where you have to do the calculation. If you go 1 centimeter into the neutron star, how much the pressure will be? It will be a staggering amount of pressure. All right. Now, as you reach a density of 10 to the power 4 grams per cubic centimeter, which you will reach in a couple of millimeters, atoms will become completely ionized. Because the atoms are rubbing into one another, atoms will melt. Now, at a density of 10 to the power 7 grams per cubic centimeter, just a couple of centimeters inside the surface of a neutron star, the free electron gas will be ultra-relativistic. Just from uncertainty principle, if you calculate the typical Fermi velocity, it will be comparable to the speed of light. Now, around this density, the Fermi energy of the electron, please remember the Fermi energy of the electron is density to the power 2 by 3. So as the density increases, Fermi energy is increasing. When the Fermi energy of the electron reaches about 1 million electron volt, please remember the Fermi energy of sodium or copper or gold in the laboratory is a couple of electron volts, 3 electron volts, 5 electron volts. So here we are talking about a Fermi energy which is 1 million electron volt. It's simply a consequence of density to the power 2 by 3. Iron 56 will no longer be the most stable nucleus. And this is because of inverse beta decay. Here is my energy bucket. Electrons are fully occupied up to that level, and that is the Fermi energy, which is of the order of 1 million electron volt or more. And an electron on top of the Fermi C can now combine with a proton to form a neutron and emit a neutrino which will escape. This is inverse beta decay. Because of inverse beta decay, iron 56 will no longer be the most stable nucleus. Then you can ask, what will be the most stable nucleus at these densities? It turns out the most stable nucleus is nickel 62. And then if you go a little further deep, it will be nickel 64. What is the difference between nickel 64, nickel 62 and iron 56? The atomic masses are roughly the same. It is the atomic charge which is varying. The number of neutrons which is varying. So these are more neutron rich. Why? Because protons inside the nucleus have converted themselves to neutron by inverse beta decay. Thus, through inverse beta decay, as you go down inside a neutron star, the nuclei become more and more neutron rich. At some stage, you will reach a density which is 4.3 times 10 to the power 11 grams per cubic centimeter. This density is something we have encountered before. This is the density Landau said, where neutronization of matter will set in spontaneously. So what you will encounter if you make a journey to, you're not gone very deep inside the neutron star, to reach this density. Okay? I leave it to you as a fun exercise to calculate at what depth you will reach that density. These are the kind of nuclei that you will encounter. Selenium 84, germanium 82, iron 76, krypton 118. Remember Superman, he came from Krypton, right? Now, these are not nuclei that you find on Earth. Because, for example, all the nuclei on the second row, there are 50 neutrons in them. So look at this, for example, 50 neutrons and only 26 protons. In our periodic table, the number of neutrons is roughly equal to the number of protons throughout the periodic table. In the next row, there are 82 neutrons. And there is something special about 50 and 82. Those of you who have studied some nuclear physics will remember these are the closed shell nuclei. So you either already know it or you'll soon study it in nuclear physics, that nuclei also have shell structure like atoms have, and these are the magic numbers. Okay, so 50 is a magic number, 82 is a magic number, just as you have 2, 8, and things like that for electronic output. So let us summarize what we have learned so far. We have said that the outer 1 kilometer, we are talking about neutron star, a model of a neutron star whose mass is 1.4 solar mass. Why 1.4 solar mass? Because we think nature makes neutron stars of 1.4 solar mass for reasons that I explained. 1.4 being the Chandrasekhar limiting mass for electron pressure supported white dwarfs. So we expect to see iron 56 lattice. As you go further down, you expect to see the neutron-rich nuclei, and at the density of 4 times 10 to the power 11 grams per cubic centimeter, the nuclei become so neutron-rich that neutrons begin to spill out or drip out of the nuclei. Remember, the electrons did that in a metal. When atoms were far away, electrons were tapped to individual nuclei. As you brought the atoms closer and closer together to interparticle distances, which are roughly the size of the atoms themselves, then the electrons leak out of individual atoms. These are the conduction electrons in the conduction band. Okay? So similar thing happens now. Neutrons escape from the nucleus and they form a fluid. So what you have as you go down in the crust is you will find a lattice of very exotic nuclei, such as the one shown above, exotic ultra-neutron-rich nuclei, sloshing around in the lattice, like electrons in metals, you will have a neutron fluid. Now this neutron fluid will not be an ideal gas of non-interacting neutrons, any more than electrons and metals are not non-interacting gas of electrons. They interact, which is why you have interesting phenomena like magnetism and superconductivity and things like that. The interaction is not very strong, but the interaction leads to exciting phase transitions. So that's what you expect. So that's what I've shown here. The inner crust will consist of, inner crust begins at a density of about 4.3 times 10 to the power 11 grams per cubic centimeter, and what you will find there, a lattice of neutron-rich exotic nuclei immersed in a Fermi liquid of free neutrons. Of course, the electrons are also there, but we are not bothered with the electrons in this case. Then, when you reach a density of 2.5 times 10 to the power 14 grams per cubic centimeter, then you are squeezing nuclei into one another, and the nuclei will now melt. In other words, the distinction between separate nuclei goes away, and what you will have is basically a fluid of neutrons and protons inside the center, like we have inside the atomic nucleus. What is the criterion that determines the composition of neutrons and protons? It is beta equilibrium. We have already discussed this, but let's discuss it again. So, about the nuclear density of 2.5 times 10 to the power 14 grams per cubic centimeter, where does that number come from? That is the density of atomic nuclei of our periodic table. Nuclei will melt. Now, the relative number of neutrons, protons and electrons is determined by the principle of equilibrium under beta decay. What does one mean by beta equilibrium? Neutrons are decaying to protons and electrons. Protons and electrons combine to form neutrons, and these two reaction rates must go in both directions by the same amount. In other words, the reaction rates have to be balanced. That is what you mean by beta equilibrium. The condition for beta equilibrium is that the chemical potential of the neutron, which is the Fermi energy at zero temperature, must be equal to the sum of the chemical potential of the protons and electrons. Or if you say since neutron stars are essentially at zero temperature, the Fermi energy of the neutron must be equal to the Fermi energy of the proton plus the Fermi energy of the electron. This condition has to be satisfied. Because please remember that all the three buckets are full up to the respective Fermi energy. All this reaction can only take place, again, your question in the beginning, only for electrons, neutrons and protons on the surface. Therefore, you have to have this condition satisfied. Otherwise, energy conservation is not satisfied. Okay? Now, if you do this, I leave this as an exercise. It should take about 10 minutes, a very elementary calculation. If you do that, you will find that roughly 5% are protons and therefore an equal number of electrons. So what you will find is 95% are neutrons, 5% are protons, and of course for charge neutrality, you must have the same number of electrons. Okay, it is similar consideration for atomic nuclei that gives roughly equal number of neutrons and protons in the periodic table. So, outer crust is iron lattice, inner crust is lattice of neutron-rich exotic nuclei immersed in a Fermi liquid of free neutrons, and then above the nuclear density you have a liquid core which consists of neutrons and protons. And what do you expect right at the center? We don't know. We'll come to that in a few minutes. Now, these pictures have been drawn based upon very sound physical principles, and there are very compelling reasons to believe in this. Now, let us ask, what is the equation of state? What is the equation of state, which is the relation between pressure and density in this region? That is, a density is less than the neutron drift density. In this region, where the density is larger than the neutron drift density, and in this region, where the density is even larger than the nuclear density. How does the pressure vary as a function of density? Now, this is a serious problem in physics. And there is no shortcut to that. You just have to go and calculate these things, guided by experiments. And there is a large industry doing this. So I will give you just a flavor. We are not going to dwell on this, but just to give you an idea, people have done such calculations over the last 30, 40 years, and these calculations are getting more and more sophisticated. First, let's consider the equation of state at densities below the neutron drift density. The problem of determining the equilibrium nucleus at any density is the same as the problem of minimizing the total energy per unit volume given a fixed baryon density and subject to charge neutrality. So this is the criterion that I am going to use. at any given depth, therefore at any given pressure. How do I say it cannot be iron 56, it cannot be nickel 64, it has to be krypton 118? What is the basis for saying all these things that I said before? The basis is determining the equilibrium nucleus based upon minimum energy consideration, because we believe the matter to have been formed in thermodynamic equilibrium. So what is the energy of a unit volume of this material? The energy of the unit volume is the energy of the nuclei. This is the number of nuclei in a unit volume. This is the energy per nucleus, whose atomic mass is A and atomic charge is Z. And this is the energy of the electrons, where NV is the number density of electrons per unit volume. So you have to calculate both these things. But as I said before, you can always regard electrons as a free electron gas, an ideal gas of Fermi particle. Therefore, given a density, I know how to calculate the energy. It is absolutely straightforward. You take any book on solid-state physics that will tell you that. The question is, how do I calculate the nuclear energy given an atomic mass and atomic charge Z, which is lowest energy configuration? Now, this is what nuclear physicists did in the 1940s and 1950s. And what you had was a mass formula, a formula for the mass of the nuclei, which will give you the lowest energy configuration. This formula was first stated by Carl von Weizsäcker, who is the one who first invented the carbon-nitrogen-oxygen cycle, which Hans Bethe then worked out for energy generation in slightly more massive stars than the Sun. So what does, if you remember from your nuclear physics studies, what is this semi-empirical mass formula? It's called semi-empirical because some of it is based on experimental data, not all of it. So what is the physical content of this mass formula? Now, what you have is a nucleus of a certain size. This nucleus of a certain size has a certain surface energy, and this nucleus, because it has protons inside it, also has Coulomb energy. And the volume energy is essentially Coulomb. So the total energy will be the sum of surface energy and volume energy. And common sense tells us that nuclei would like to have as little surface energy as possible and as little as Coulomb energy as possible, because this is repulsive energy between the protons inside the nucleus. What does nuclear physics tell us? What is the mass formula? The mass formula says that the surface energy of the nucleus is proportional to A to the power minus 1 by 3. You either know it or you please accept it, where A is, of course, the total number of nucleons inside the nucleus. And that is in the denominator. Therefore, larger the nucleus, smaller is the surface energy. Larger is the nucleus. Obviously, a small liquid droplet has more surface energy than a large liquid droplet. Right? So, surface energy would favor large nuclei. But on the other hand, Coulomb energy, which is proportional to Z squared, the correct expression is A to the power 2 by 3 Z over A whole squared per nucleon, because that is a repulsive energy between protons. would obviously favor small nuclei. Therefore, Weizsäcker's mass formula tells you that the most stable nucleus is likely to be the one where there is a balance that determines the atomic mass of the nucleus. Yes?
The nuclear radius is proportional to a to the power 1 by 3, right?
Surface energy.
No, actually nuclear radius is just R naught in.
That's right, that's where it comes from.
That's why 4 pi R square gives us.
Okay, but this is, I'm talking only about the dependence on A. I'm not putting all these other factors. No, you please look into it, we can discuss it. I'm not saying this is the expression for surface energy. That is where you're challenging me. I'm not saying this is the expression. So I'm saying nuclear surface energy favors large nuclei because in the surface energy you have a term which is proportional to 1 over A to the power 1 by 3. And that obviously favors larger A. These are not the expressions for the surface energy or the volume energy. I'm talking about the dependence on A. I'm trying to see I'm merely trying to suggest that one favors large nucleus, one favors small nucleus, and the balance will give you the lowest energy configuration. So if you would like to understand this, writing it differently, please do that, okay? Because my purpose was not to write the expressions for the energy themselves. This expression for the surface energy, volume energy are all to be found in standard books on nuclear physics. Now, how was this problem approached by people? John Wheeler in Princeton and his variety of collaborators, starting with Harrison in 1958, they regarded the atomic mass A and the atomic charge Z as continuous variables. So, because here for the neutron star problem, as you go down, they said we'll treat A as a variable and Z as a variable, and therefore go from one depth to the neighboring depth. Then a few years later, Salpeter, who was working with Hans Bethe in Cornell, said, no, wait a second, you can't regard A and Z as continuous variables because there is such a thing as shell structure in the nucleus, certain values of A and Z are favored. So Salpeter brought a certain degree of refinement to the Harrison-Wheeler picture. And then Bain, Pethick and Sutherland, working with Hans Bethe, said, but what you guys have forgotten is that the nuclei are arranged in a lattice and there is an interaction energy between the various lattice points, and also there is interaction energy between the lattice points and the electrons, and between and you have to take this into account. If you take, for example, a solid, like a terrestrial solid, this lattice energy is very important, extremely important. A very important part of the cohesive energy of metals. So what they said was, look, the lattice energy is of the order of minus Z squared E squared over A, where A is the lattice spacing, not to be confused with the atomic mass, A, capital A. So what they said was, this lattice energy, because it is minus sign, reduces the Coulomb energy, which is repulsive, and thus favoring a slightly larger nuclei. Remember what I said, the repulsive nature of the Coulomb energy prefers smaller nuclei, and what Bain et al. Said is that if you include the lattice energy, you can actually tolerate a little more massive nuclei. Again, I'm not trying to teach you these things, I'm just taking you on a journey how people approach this problem during the last 30, 40 years, how sophistication increased gradually. So what is plotted here, not to be looked at in detail, I certainly am not going to discuss it, is the logarithm of the pressure on the y-axis and the logarithm of the density on the x-axis. So for example, this CH stands for the Chandrasekhar equation of state, which is the ideal Fermi gas equation of state. Density to the power 5 by 3 or relativistic regime 4 by 3. So you notice that there are deviations from the Chandrasekhar's equation of state, Harrison, Wheeler, Bohm, Pettit points, and so on. So I merely want to say that taking into account all these effects does make a difference, and this is a log plot. So the small deviations are of great consequence. Now let us look at the equation of state above the neutron drift. That means that densities larger than 4 times 10 to the power 11 grams per cubic centimeter, but smaller than the nuclear density of 2.5 times 10 to the power 14 grams per cubic centimeter. Now again, Bain, Bethe and Pettit used the semi-empirical mass formula, but they brought in a very important new effect into play, namely many-body effects. Because in this region, please remember, a density greater than 4.3 times 10 to the power 11, you have a sea of neutrons outside the lattice, like you have a sea of electrons inside the metal. Now, Landau and then a whole large number of people all over the world spent 20, 30 years trying to understand many body effects of these electrons in metals. In following in that footsteps, Hans Bethe and his young colleagues tried to incorporate many body effects between the electrons into these calculations. As we will soon see, these many body effects lead to very dramatic properties like superfluidity and superconductivity and so on. Now, what about the liquid interior? A density larger than 2.5 times 10 to the power 14 grams per cubic centimeter. There one derives the nuclear potential from scattering experiments. Please remember, if you're dealing with inside the atomic nucleus, the only thing you have guiding you are experiments, collision experiments, and accelerators like CERN and other colliders. This tells you what the nuclear potential energy is as a function of distance and therefore as a function of energy. Now you have to solve the many-body Schrodinger equation and not single-particle Schrodinger equation. These are extremely complex calculations, and one has to include 3-body forces. Now this was first discussed 3-body and 4-body forces. Remember, normally we discuss only 2-body forces. Now, Professor R. Raja Raman, who used to be in the Indian Institute of Science here, then went to JNU in Delhi, when he was Hans Bethe's PhD student, his thesis was on inclusion of 3-body and 4-body forces, nuclear forces into the calculation of equations of state. And again, I only want to show here logarithm of the pressure on the y-axis and logarithm of the density. And you see, this is the Harrison-Wheeler curve on the top, which does not include many body effects. And you see the inclusion of many body effects significantly alters the equation of state. Again, I stress this is a log plot, therefore now those differences are enormous differences. But we are not going into that. I just want to tell you that people have not just been waving their hand, they've been doing very hard calculations for the past many decades. Now, what about exotic states near the center of a neutron star? So far, we have talked only of the 2 baryons, neutrons and protons, and 1 lepton, which is the electron. The question is, as you go towards the center of the neutron star, are you likely to encounter particles like pi mesons, k mesons, and even more exotic particles like the quarks? I mean, after all, we have seen all these particles in experiments, and they are produced at higher energies. And as you go towards the center of a neutron star, you are going to higher and higher pressure, therefore higher and higher energies. So let us approach this problem from the point of view of basic physics, because that is all we can do, and then be guided by observational astronomy. Now, pi mesons, as we discussed when we were talking about gamma rays and atmospheric interaction, comes in 3 varieties: pi plus, pi minus, and pi 0. The mass of the pi meson is roughly 140 million electron volt. They obey Bose-Einstein statistics. unlike electrons, protons, and neutrons. And let us recall what we have done so far in the liquid interior. We had invoked the criterion of beta equilibrium, which says that the Fermi energy of the neutron must be equal to the sum of the Fermi energy of the proton and the Fermi energy of the electron, or more correctly, chemical potential. But I stress at low temperature, they are the same thing. Now, the point is, this sea of neutrons and protons and electrons will spontaneously produce pi mesons when you reach a certain critical density. And the critical density is that the chemical potential difference between the neutron and the proton, when it exceeds the rest mass energy of the pi meson, instead of electrons in beta equilibrium, you will suddenly start producing particles which are 140 times more massive than the electron, namely the pi meson. And this is a spontaneous production. Okay? So, in other words, previously the electron here combined with a proton to form neutrons, which was inverse beta decay. Now what we are saying is, this is the Fermi energy of the neutrons, and when the Fermi energy of the neutron increases above a critical value, neutron can decay to protons, and not electrons, but protons and pi mesons. And what does theoretical nuclear physics suggest? It suggests that this is likely to happen around twice the nuclear density. What is the nuclear density? 2.5 times 10 to the power 14 grams per cubic centimeter. So this is likely to occur at about 5 times 10 to the power 14 grams per cubic centimeter. Now, this too depends on who you talk to, whether they have included many body effects, whether they have included all kinds of polarization effects and so on. So the 2 may be 3 times the nuclear density. That is where the uncertainty comes in. Now what happens if you go to even higher density? Something can happen. This is just a repeat of what we said. That is around twice the nuclear density. The chemical potential difference between neutron and proton can exceed the mass of the pi meson, and therefore pi mesons are spontaneously produced. But at a higher density of 3 or 4 times the nuclear density, you produce K mesons, which are more heavy than the pi meson. The point is, these are all spontaneous productions of pi mesons and K mesons. So instead of beta equilibrium, you have pi meson equilibrium or K meson equilibrium. Now, the important thing to appreciate is that if these particles, the pi mesons and K mesons, do occur inside a neutron star near the center, then they can have very dramatic consequences, observational consequences. These arise due to the fact that pi mesons and K mesons obey Bose-Einstein statistics. Now, to recall for you, I have written down the equilibrium distribution, the probability of occupancy of energy Ek in both the Bose-Einstein statistics and the Fermi-Dirac statistics. There are 2 notable differences. The first difference is, in the case of the Fermi-Dirac distribution, there is a +1 in the denominator, whereas in the Bose-Einstein statistics, there is a -1 in the denominator. The second fundamental difference between the two is that the chemical potential of the Fermi gas, which is Fermi energy at 0 temperature, is a positive quantity. Whereas the chemical potential of a Bose-Einstein gas has to be negative. It can at most be 0, but it can never be positive. And this results in some dramatic consequences. And that phenomena is known as Bose-Einstein condensation. It's a bit unfair because Bose had nothing whatsoever to do with any of these things. Bose did not even appreciate that the statistics that he had discovered applies to other particles too. That was all Einstein. And when Einstein, if you remember the history, Bose, when he discovered the statistics of the photon gas, sent it to Einstein, and said, could you please have it published in a German journal? Which of course Einstein did. But while reading through Bose's paper, Einstein realized that this statistics applies to particles with other integral spins, and in particular to helium nuclei. And then he submitted a paper immediately, and in that paper itself, he pointed out that there will be this phenomena of condensation. So it should really be called Einstein condensation and not Bose-Einstein condensation. Now, what are the properties of a degenerate Bose gas? In other words, a dense Bose gas at very low temperature. We know what the properties of the Fermi gas are at very low temperature. Now, the behavior of the Bose gas at T equal to 0 is very different from that of the Fermi gas. We already saw that a Fermi gas at 0 temperature has a very large 0-point energy, and that supports the star. Those are the white dwarfs and neutron stars. But in a Bose gas, at temperature T equal to 0, all the particles will be in the state E equal to 0, like in classical statistics. All particles will have 0 energy. And the second difference is that Bose particles do not have to obey Pauli's exclusion principle. Please remember that the large energy of the electron gas arose from Pauli's exclusion principle because you could only put 2, 2, 2, 2. Now, if you could put all of them in the 0 energy state, then the total energy of a Bose gas at 0 temperature is 0. And therefore, the total pressure of a Bose gas at 0 temperature is 0, like a classical gas. And that, of course, has disastrous consequences for a star. Now, this fundamental difference between the Bose gas and the Fermi gas arises due to the fact that for a Bose particle, the chemical potential has to be negative. For a classical gas, like the Boltzmann gas, Maxwell-Boltzmann gas, the chemical potential can be either positive or negative. But for a Fermi-Dirac statistics, the chemical potential has to be positive, and for Bose-Einstein statistics, it has to be negative. Now, what is this phenomena of Bose-Einstein condensation? Let us say I have n Bose particles at a temperature T. And the statement is that there is a critical temperature which we will call T0 or Tc for this problem. At a temperature below this critical temperature T0, the number of particles whose energy E is greater than 0 is n into T by T0 to the power 3 by 2. This result can be found in all books on statistical mechanics. You have probably studied it. In other words, the number of particles with energy E equal to 0 is the total number n minus the number of particles with energy E greater than 0. So the important thing for us to appreciate is that in Bose statistics, the number of particles with 0 energy is n into 1 minus T by T0 to the power 3 over 2. Therefore, at T equal to 0, this term vanishes, and the number of particles with energy E equal to 0 is equal to the total number of particles. In other words, the entire gas collapses to the 0 energy or the 0 momentum state. And that is the phenomenon of Bose-Einstein condensation. And please appreciate that this is not a condensation in real space like this. Water is a condensation of molecules in real space. That is a condensation in momentum space. It's still a gas sloshing around, but in momentum space, they all occupy 0 momentum. Now, let us go back to pions for the moment. Pi mesons and K mesons, all mesons obey Bose statistics. Therefore, at very low temperature, what is very low temperature? T less than T naught, and T naught will have a formula. The number of particles in the momentum state, here I called it Tc by mistake, this is T naught. This T naught is given as density to the power 2 by 3, h bar squared divided by m. And this is Boltzmann's constant, Kb. Therefore, given a certain density of pi mesons or k mesons or helium nuclei, I can calculate what this critical density is, and the statement is that the temperature below the critical temperature, there will be a large number of particles in the zero energy state, and at T equal to 0, the pi mesons will all be in the zero momentum state, and the equation of state will be soft. In other words, the equation, the gas will be highly compressible, and therefore the star will collapse. So, if this phenomena actually happens, then we have to slightly modify our picture and say that deep inside the neutron, proton, electron fluid core, if the density ever reaches 5 times or 10 times the nuclear, 10 to the power 14 grams per cubic centimeter, then you may find pi mesons. And if the density reaches even a higher value, you may find k mesons. Now, do the densities of actual neutron stars actually reach these values? There you have to be guided by observations. Okay? Observations of pulsars and observations of X-rays from neutron stars. Why? Because if pi mesons and k mesons condensates occur, remember, if they occur, they will be condensate because the temperature is very low. They will have very high neutrino luminosity, and therefore neutron stars with pi mesons and k mesons will cool much faster than neutron stars without pi mesons and without k mesons. Now, what do observations tell us so far? Observations tell us, particularly after the launch of the Chandra X-ray Observatory, with which you can detect the black body X-ray emission of neutron stars. Because neutron stars, even which are thousands and thousands of years old, are still many millions of degrees hot, and an object of millions of degrees will radiate X-rays. Black body spectrum will peak in X-rays, and these are seen by Chandra X-ray Observatory. And the fact that you're able to see X-ray, black body X-ray emission from very old neutron stars suggests that neutron stars do not cool very rapidly. And therefore, this argues against pi mesons and k mesons. Similarly, there are other considerations which we can come to if you're interested. Somebody can ask me in the next lecture, which is on millisecond pulsars. So there are other constraints which come from millisecond pulsars, which tells us that the equation of state of neutron stars is actually very stiff and not soft. In other words, it argues against the occurrence of these objects. Now, what about the very center, where there is this question mark? Now, the very center, you are reaching temperature, energies, densities, and therefore energies, and therefore equivalent temperatures of the order of 10 to the power 12 Kelvin, which is the sort of temperatures that obtained in the early universe when the universe was less than about a second old. Now, according to prevailing theories of elementary particles, and we will touch upon this in the last lecture next Wednesday when we discuss the early universe, it has been conjectured that when the universe was hotter than about 10 to the power 10 Kelvin, there were no neutrons, there were no protons, there was just a soup of quarks. And as the universe cooled to a certain critical temperature, by virtue of expansion, quarks, bound states of quarks formed, and that's what you call neutrons and protons. So the same thing you would expect going in the opposite direction. As you go towards the center of the neutron star, you're going to higher and higher density, therefore higher and higher temperature, and therefore you can ask, first we had atoms that melted, then we had nuclei that melted, and now what we are saying is neutrons and protons, if you squeeze them hard enough, they can also melt, and their constituents are quarks. So you can ask, are you likely to find a soup of quarks, and what binds them, which are the gluons, at the center of a neutron star? Now, according to predictions of elementary particle physics, this is likely to happen only at densities in excess of about 5 or 10 times the nuclear density. So we are talking of densities of the order of 10 to the power, several times 10 to the power 15 grams per cubic centimeter. And please remember the great uncertainty of these temperatures, because it's not so easy to predict a precise density where this quark hadron transition occurs. But very serious theoretical physicists have speculated that not only you'll have quarks at the center of neutron stars, once some quarks form, whole star will become a star of quarks, strange stars, for reasons that I have never understood, but these are all speculations. And please remember, however eminent the physicists may be, speculations are speculations. Now, what can we say at the moment? At the moment, one can be very sound and be a Rutherford and say, to hell with theoreticians, I'm going to be guided by experimental facts. And what do experimental facts tell us? One of the things is that the quarks, if they occur, they will have an even higher neutrino luminosity than the pi mesons and k mesons, this theory tells you. And therefore, X-ray emission from neutron stars may be inconsistent with the formation of quarks, right at the center. But if you're talking of the whole star becoming a star of quarks, what they call strange stars, a variety, many different varieties, I think there is very strong observational evidence to suggest this cannot be the case for neutron stars. And the reason is this. According to these people who predict quark stars, these quark stars are not expected to have a crust. But I know neutron stars have a crust because they anchor magnetic fields and they produce periodic pulses which are highly stable. Therefore, if you ask me, I would bet against strange stars like quark stars simply based on this consideration. This plus observations of millisecond pulsars spinning with a period of 1 millisecond, 1.5 milliseconds suggests that the equation of state of neutron stars is in fact very stiff and not at all soft. So I would say that at the moment, it seems very unlikely that you are going to encounter either pi mesons or k mesons, let alone quarks, as you travel down to the center of a neutron star. But then the last word has not been said on these things. So I would still insist on retaining this question mark over here. Now, we change the subject now. Now we go to discuss superfluidity in neutron star. Now this probably will surprise you because superfluidity on Earth is an extremely low temperature phenomenon. Now, you're talking of stars with interior temperatures of 100 million degrees. It is nonsense to talk of superfluidity, not at all, for reasons that I have already stated. Neutron stars are very cold objects. Now, let us recall the spectacularly successful theory of superconductivity due to Bardeen, Cooper, and Schrieffer. Now, as you know, superconductivity was discovered by Kamerlingh Onnes in 1911 as soon as liquid helium was discovered. He found that metals became superconductors. Many great physicists like Heisenberg, Pauli, Landau, Feynman, everybody and his grandmother tried to solve this problem of superconductivity. But finally it was solved by Bardeen and Leon Cooper and his student Bob Schrieffer in 1957. It's a very strange story connected with this, which was told to me by Bob Schrieffer the day after the Nobel Prize was announced for this thing. Nobel Prize was awarded for this in Sweden. I happened to be working in Sweden at the time. So Bardeen and his students, Cooper was his postdoc and Schrieffer was his student, they were working on this theory and they were almost there. And Schrieffer had constructed the wave function for the superconducting ground state and went and showed it to Bardeen, and Bardeen simply looked at it and said, this cannot be right because what you have constructed is a fermion ground state. I know that the superconducting ground state must be a bosonic ground state. Go and check your algebra. Just at that time, there was a phone call from Stockholm. Bardeen had been awarded the Nobel Prize for the discovery of the transistor. And he didn't want to go to receive the Nobel Prize because they were so close to solving this problem. And of course, they did solve this problem and he was awarded the second Nobel Prize for this many years later. Now, what is the underlying physics of this theory? I think it is important to mention that this theory of Bardeen, Cooper and Schrieffer is the most spectacularly successful of all many-body theories of either electrons or nucleons or elementary particles, whatever it is. It is the most successful many-body theory till today. Now, at the base of this theory, the point is that electrons obey Fermi-Dirac statistics. So if you want something like a phenomenon of superconductivity to occur, you have to form Bose-Einstein particles. And the way it was done is that Cooper found that two electrons on the opposite side of the Fermi sphere, P and minus P, PF and minus PF, form bound pairs of molecules, not in physical space but in momentum space. These are called Cooper pairs. And in some sense, these Cooper pairs condense and produce these super properties, in this case, superconductivity. Now, the underlying physics of this Bardeen-Cooper-Schrieffer theory is that although the interaction energy between two electrons is repulsive, strongly repulsive, if electrons talk to each other through lattice vibrations, quantized lattice vibrations known as phonons, then this interaction between electrons mediated by phonons can be attractive. It's only attractive by a very small amount. But even that very small amount, as long as it is attractive, enables two electrons on the opposite end of a diameter of Fermi sphere with oppositely pointed spins can form these Cooper pairs, and this phenomena of superconductivity is an immediate consequence. Now, why is superconductivity an extremely low temperature phenomenon? Now, the thing to appreciate is that the existence of the Fermi sea, the Fermi sphere, inside which all states are occupied and outside which all states are unoccupied, guarantees the formation of Cooper pairs. No matter how weak the interaction is, as long as it's attractive. Now the point is, this attractive energy between two electrons mediated by the lattice is of the order of milli-electron volt. whereas the energy of interaction, repulsive energy of interaction between electron is of the order of electron volt. So this is 1000 times less. Okay, 1 electron volt is 10,000 degrees. A milli-electron volt is about 10 Kelvin. And that is why superconductivity is a low temperature phenomenon. A superconductor is a low temperature phenomenon because the energy gap between the normal metal and the superconductor is only of the order of milli-electron volt. A milli-electron volt is about 10 Kelvin. So if you go to higher temperature, these molecules that you have formed of electrons break up. Now, one of the important things appreciated by Bardeen very early on is that a superconductor is not just a metal with zero resistance, as many people had thought. He appreciated that a superconductor is a very different thermodynamic state because it is a perfect diamagnet. And that was established long ago in 1933 by Meissner, who showed that if you had a metal through which a magnetic field passes, and if you cool that metal and the metal becomes superconducting, it expels the magnetic field. In other words, it's a diamagnet. Here is a magnet, here is a superconductor, and the magnet is levitating above the superconductor. Okay? This is important for our discussion in tomorrow's lecture. So, what is the fundamental property of superfluidity and superconductivity? The fundamental property is that it has a long-range order. A crystalline lattice has long-range order. If I know there is an atom here, then I know exactly where the millionth atom is going to be. Similarly, a ferromagnet has long-range order. The spin orientation is coherent. If I know the spin orientation at one point, then I know it at every other point. Now, in a perfect lattice, you would have studied these things in your first chapter of solid-state physics. In a perfectly crystalline solid, the wave function for the electron, psi k of r, can be written as an amplitude uk of r multiplied by e to the ik dot r, a plane wave. The point is that this amplitude is a periodic function. In other words, the amplitude at r is the same as the amplitude at r plus a, where a is the lattice constant, the same as amplitude at r plus 2a, 3a, 17a, and so on. Okay? So in a perfectly periodic lattice, the wave function of the electron is phase coherent. Metals have resistance because this perfect phase coherence is destroyed by various scattering by impurities, etc., etc. So the wave function is phase coherent. Now in a superfluid, the wave function of a superfluid is again an amplitude multiplied by a phase, e to the I theta. Now, according to the theory of superconductivity, the superfluid velocity, what you call as the superfluid velocity, Vs, is the gradient of the phase of the wave function. Okay? This comes from the basic theory, which I have in fact indicated over here, there, but we won't go into that. So there is this concept of a superfluid velocity, like there is a concept of velocity of an ordinary fluid. And that velocity is the gradient of the phase of this wave function. Now once again, this wave function is phase coherent, or there is long-range order. And that long-range order is a fundamental property of all these ordered states, as was first pointed out by Landau. Now, as soon as Bardeen-Cooper-Schrieffer theory, this story as told to me by Bardeen himself many, many years ago, is that he had met the great Russian physicist Bogoliubov somewhere in America and had given him a copy of his paper. Remember those days in Russia, I mean, Soviet Union, there wasn't much for Western journals were not going there and so on. So Bogolubov reached Moscow and gave a copy of this paper to one of the guys working in Landau's group. And as soon as they all sat together and read this paper, and immediately applied it to neutron stars. And within a matter of 3 or 4 days, the story I'm going to tell you was stated. Okay. All they needed was this theory. Of course, Landau was beaten to this theory by Bardeen and his people. One of Landau's students, A.B. Migdal, applied the Bardeen-Cooper-Schrieffer theory and argued that the protons inside the neutron star will be superconducting. So that was stated within 2 years after the Bardeen-Cooper-Schrieffer theory. Soon after that, Ginzburg and Kirchnitz argued that the neutrons will be in a superfluid state. Now, please notice that both these predictions were made many years before the discovery of neutron stars, because in 1957, nobody believed in Chandrasekhar limits. Nobody believed in Oppenheimer-Volkoff results. Why should they believe in neutron stars? Nobody had seen neutron stars, right? And neutron stars were relegated to one chapter in Landau and Lipschitz statistical physics. And like everything else, so many other things, just because it was a possible state of matter, they worked out everything that you can work out about it. And then we are talking about it 70 years later, right? Now, 50 years after this, Ginzburg was awarded the Nobel Prize, not for this, but for his contribution to the superconductivity of metals. Now, let's consider superfluid states in neutron stars. Superfluid states meaning superfluidity of neutrons and superconductivity of protons. They're all related. Now, please remember, to have either a superfluid, see, the case of helium is straightforward. Helium nuclei obey Bose statistics because there are 2 protons and 2 neutrons. But if you want to start out with fermions, like in a superconductor, you have to take fermions and make molecules out of them to make bosons. And that we saw was very difficult, very, very weakly bound pairs, which is why superconductivity is a very low temperature phenomenon. But here, the interaction, please remember, the temperature at which something becomes superfluid, or the temperature at which some metal becomes a superconductor, is determined by 2 things. It is determined by the strength of the attractive interaction between the fermions, and it is determined by the number of states, allowed states at the Fermi level, the density of states of the Fermi energy. So these are the 2 things. So according to the Bardeen-Cooper-Schrieffer theory, the transition temperature is related to the Fermi temperature by e to the power minus 1 over the density of states of the Fermi energy multiplied by the strength of the attractive interaction. Now, in the case of superconductor, the attractive interaction, the Cooper pairs, is very weakly bound, very weakly bound. But 2 neutrons and 2 protons naturally attract one another due to nuclear forces, and that attractive force is enormously strong. Therefore, this transition temperature is not a few Kelvin, but an astronomical number like 10 to the power 7 or 10 to the power 8 Kelvin, or more than that. Anyway, I written down somewhere. So the point is, nuclear forces between nucleons is strongly attractive. Therefore, superconductivity and superfluidity of the neutrons and protons are far more natural consequences than for electrons and metals, where you have to do all sorts of subtle things to make them weakly attractive. And then, of course, superconductivity follows. So the transition temperature that you calculate using Bardeen-Cooper-Schrieffer theory is of the order of 10 to the power 9 or 10 to the power 10 Kelvin. Therefore, once the neutron star has cooled, interior of the neutron star has cooled below this temperature, superfluidity and superconductivity will set in spontaneously. That means literally within days after the formation of neutron stars, you have to believe that the interior has become superfluid and superconducting. So let me stress once again, the name of the game people, solid-state physicists are struggling is to push this transition temperature of metals to room temperatures. Because the moment you can have room temperature superconductivity, it will change the world. And here you're talking of a transition temperature of 10 to the power 10 Kelvin. So all I'm saying is, don't doubt superfluidity and superconductivity in neutron stars. The reasons are absolutely compelling because this Bowden-Cooper-Schrieffer theory is a spectacularly sound theory. Okay? All right. Therefore, as Ginzburg and Kirchner said, neutrons will be in a superfluid state and protons will be in a superconducting state, but the electrons will not become superconducting because of very high temperature and their light mass. Okay? So electrons remain normal, degenerate, relativistic fluid. I mean, that was also stated by Ginzburg, that the electrons will be normal. Now, I want to tell you about something very interesting that happens to the superfluid and also to the superconductor. First, let us consider a beaker with superfluid helium and we rotate that beaker. Now, if you rotate a bucket of water, what happens is, for a while, the water doesn't rotate, only the bucket rotates. But because of viscosity between water and the bucket, slowly the water also starts rotating, and the angular velocity of rotation of the water would correspond to rigid body rotation of the bucket. That does not and cannot happen for a superfluid, for the following reason. A superflow, that means flow of a superfluid, is a potential fluid in the sense it cannot support circulation. It cannot support circulation. It cannot support circulation because the curl of the velocity, which is circulation, is by definition zero. Why the curl of the velocity of a superfluid is zero? Reason is very simple. Remember that the wave function of a superfluid is psi of r is the modulus of psi e to the power I theta r, where theta is the phase of the wave function. We also defined that the superfluid velocity is the gradient of the phase of the wave function. And as you know, the curl of the gradient is zero. Therefore, the superfluid cannot rotate. Therefore, there is a serious problem. So if I have a bucket of superfluid, and if I rotate the bucket, thermodynamics tells me the free energy will be lowest if the superfluid also rotates. It's simple common sense. But quantum mechanics tells you that the superfluid cannot rotate. So this was a great problem in physics for a very long time. And this problem was finally solved by two people independently. It was first solved by Lars Ansager in Norway in 1949 and Feynman later on in 1956. So if you read Feynman's biography, you will find that he's very proud of this, and rightly so, because this was a very spectacular thing. But I think it is important to appreciate that this problem was cracked long before that by Lars Ansager. I don't know how many of you are familiar with this name, Ansager. You might have encountered his name, for example, as a person who produced an exact solution for the two-dimensional Ising model of the magnet and so on. But he was a very great man. I think he wrote only 21 papers in his lifetime, and I think 3 of them deserved Nobel Prizes, and 1 of them did get him a Nobel Prize. He was a very great chemist and physicist. Now, what did they say? What they said was, if you rotated a bucket of superfluid helium, Quantum mechanics tells us that this superfluid cannot rotate as a rigid body because the curl of the velocity is zero. And yet thermodynamics says it should minimize the energy by mimicking rigid body rotation. So what Ansager and Feynman said is that the superfluid will pierce itself with numerous needle-like structures. Inside each of those needles, it destroys superfluidity, and therefore there can be a circulation around that needle. But then we are dealing with quantum mechanics. This circulation cannot have any value, just as angular momentum cannot have any value, must have multiples of Planck's constant. This circulation must be multiples of h over 2m, where m is the mass of the particle. Why 2m? Because two particles join together to form a Bose particle, so that's where the 2 comes from. So, instead of rigid body rotation, a superfluid pierces itself with numerous quantized vortices. Why am I calling them quantized vortices? Because the circulation of each individual vortex is Planck's constant divided by the mass of the particle. So obviously, if I rotate the bucket slowly, I need to create only a few vortices. If I rotate the bucket faster, I need to create more vortices. So what is the equation governing the number of vortices? Very simple. Let us rotate this bucket of radius capital R with an angular velocity capital omega. The circulation is the integral v dot dl. If r is the radius of the bucket, then this integral gives me 2 pi r, which is the circumference of this bucket, multiplied by omega r. So if I rotate a bucket with a specific angular velocity omega, that is the circulation. What is the circulation of individual vortices? H divided by 2m. Therefore, capital N of V is the number of these quantized vortices. So that equation here tells you, you tell me the radius of the bucket, you tell me the angular velocity of the bucket, I will tell you exactly how many vortices there has to be. If I spin up the bucket, more vortices will come. If I put my hands on the bucket and slow down the bucket, some vortices will disappear. At every instant of time, the number of vortices must be given by this equation. Now, if this bucket is 10 kilometers in radius, spinning with a period of 1 second, like a neutron star, this formula tells me there will be 10 to the power 16 Ansager-Feynman vortices. Okay, so this was the prediction made in 1949 and 1956 by Feynman. And then by 1964, Ginzburg had applied all this to a neutron star. Ginzburg had not only said the neutrons inside a neutron star will be superfluid, he said this neutron superfluid will be in a vortex state. Okay? In a paper by Ginzburg actually discusses this vorticity. But of course, this is all figment of imagination. Then, many years later, a young man in Berkeley University, in 1971, actually rotated a beaker of superfluid helium faster and faster and faster and faster, and he noticed quantized vortices appearing, and they become larger in number. The number has to be always proportional to the angular velocity. Each vortex has a quantum of circulation h divided by 2m, and you see these vortices forming a nice periodic lattice. So when Feynman saw this paper in Physical Review Letters, he sent a postcard to this author, and this is all the postcard said. Visions in the head at night 20 years ago, coming out in black and white reality. and the year was 1971. So it took a long time from 1949 on Sagar's paper, Feynman's paper of 1956 and Ginzburg's paper of 1964 before these quantized vortices were actually found. These are very, very difficult experiments to do, which is why it took a very long time. But today, I can have a gas of atoms, I can cool them using laser beams to nano-Kelvin temperatures and make them undergo, become a Bose-Einstein condensate. Then I can spin this little droplet using magnetic field, and I can set up vortices in them. Believe it or not, this can be and has been done. There it is. It's a droplet of Bose-Einstein condensate. As you rotate it, vortices appear, more in number, more in number, more in number, more in number, and the interaction energy between these vortices, like in solids and so on, makes them form beautiful lattices to lower the free energy. Okay? Here is another picture. Okay? So you have to believe all this, this is not just science fiction, these have been seen experimentally. So now, what actually happens is that if you rotate a bucket of superfluid, it doesn't rotate like a rigid body. This is what it does, but from a macroscopic point of view, V as a function of R will be a straight line like this, which is rigid body rotation. So a superfluid will mimic rigid body rotation by creating these vortices. Okay, this is all experimentally proved now. So now let us look at neutron superfluidity inside a neutron star. If it occurs, and I believe in this very strongly because the reasons are compelling. See, the question is, why does one have doubt sometimes? You calculate a transition temperature on 10 Kelvin, you're unsure if it could be 8 Kelvin or 17 Kelvin. But here you're talking of a transition temperature of 10 to the 9 or 10 to the 10 Kelvin. Even if I'm wrong by a factor of 10, I'm comfortably, below that temperature. That's what I mean by saying the reasons are compelling. And I don't have to do any subtle mechanism to pair the neutrons and protons. Nuclear forces do it naturally. Now, one of the consequences of this neutron superfluidity is that they are at the base of star quakes. Pulsars have quakes in them, like Earth has earthquakes. And what one believes is the reason for these quakes is that as the bucket of superfluid slows down, as the neutron star slows down, because it's emitting energy and angular momentum, the period of rotation of the neutron star will increase. The number of vortices will have to decrease because at every angular velocity, the number of vortices is uniquely defined. Now, due to various processes of pinning and unpinning, this motion of vortices outward is somewhat jerky, and this jerky motion suddenly gives rise to star quakes. And when a star quake occurs in a neutron star, it releases an enormous amount of energy. So translated to Richter scale, it could be of the order of 50 on the Richter scale, or 40 on, I may be wrong in that. You can calculate, 10 to the power 34 ergs is released in a quake in a Crab pulsar or Vela pulsar. Translate that to the Richter scale, you'll get a very large number. Okay, that is the point. It doesn't matter if it's 56 or 46. Now, how do we know this is all got to do with superfluidity? And the reason is, if you have, for example, earthquakes on Earth, then we know the recovery happens within a matter of days. There are aftershocks and so on, that there is a recovery. The Earth once again starts spinning, so that the length of the day is once again 24 hours. But the recovery timescale of a neutron star after such a quake takes a year or two. That slow recovery, very serious people like P.W. Anderson and others have worked on this problem and have convinced themselves this very long recovery timescale cannot be understood by any other mechanism than appealing to superfluidity of the interior. If the interior was a classical fluid, then time scale will be of the order of hours and not a year or two. Okay? There's simply no way to construct a time scale of the order of a year or two without invoking superfluidity. Now let's come to the proton superconductor. McDowell had predicted protons in a neutron star will be superconducting already in 1959. And although the reason for proton superconductivity is compelling, the neutron star will be faced with an embarrassing dilemma. What is the embarrassing dilemma? It is the following. Neutron stars, when they are born, have strong magnetic fields. Why do they have strong magnetic field? Because the star from which they collapsed and formed had magnetic fields. Why did they have magnetic fields? Because there were convective currents which led to magnetic fields. We know white dwarfs have magnetic field of the order of 1,000,000 Gauss. So white dwarf collapses, you'll get 10 to the power 12, 10 to the power 14, 10 to the power 15 Gauss. So, as the neutron star cools down, it would like to become a superfluid, and it becomes a superfluid. There is no problem. So the bucket is rotating, no problem, it forms vortices. But as the neutron star cools down, as the protons cool down, they would like to become superconductor. But they are stuck with this magnetic field. Superconductor has to be a perfect diamagnet. And I showed you a picture of how the magnetic field is expelled. So you'll say, why doesn't the star expel the magnetic field? Very straightforward. Happens all the time in the laboratory. Well, it can't, because the magnetic field is created by the electrons. So only way to expel the magnetic field is to push out all the electrons. So if you separate electrons from protons, you will create such an enormous electrostatic field that it's simply not on. So the superconductor has to do something clever, become a superconductor, and learn to live with a magnetic field. This is not an unusual situation. Because when most alloys become superconductors, this is what they have to live with. And this problem was also studied in Landau's group at the same time in the 1950s. And this problem was studied. So this is what I said. This problem was studied by Abrikosov, who was one of Landau's young students. Now, there are two types of superconductors, and people are very clever and imaginative. They're called type 1 and type 2. Type 1 superconductors are pure metals, like mercury, lead, tin. But then alloys, now, previously one thought only some special metals become superconducting. Now we know that every metal becomes a superconductor, as long as it's a question of to what temperature do you have to cool it. Several degrees, millikelvin, microkelvin, but now we believe all metals will become superconductor. Alloys too become superconductor, but alloys, there is something very strange. Now, what you find in this type 2 superconductor is that this is the transition, this is the temperature, and this is the magnetic field. When the magnetic field is very small, the superconductor expels the magnetic field. There. Meissner effect, perfect diamagnet. When the magnetic field is here, then of course superconductivity is destroyed. So the magnetic field penetrates the field. So the question is, in between these two critical fields V1 and V2, what does a superconductor do? The metal has a magnetic field frozen into it. It wants to become a superconductor. How will it cope with this? This problem is reminiscent of how does a beaker of superfluid cope with rotation. Rotation and magnetic fields are very similar phenomena. So Abrikosov pointed out that a superconductor will do exactly what the rotating bucket of liquid helium will do. It will destroy superconductivity in quantized regions and therefore allow magnetic field to go through it. But then the amount of magnetic field, that flux that goes through each needle has to be quantized. because you're dealing with quantum mechanics. Superconductivity is a manifestly quantum phenomenon. And Abrikosov wrote this paper in 1958, but he wasn't allowed to publish that paper by his guru, Landau. Very terribly clever people like Pauli and Landau made this mistake many times. They made colossal mistakes, and their young colleagues suffered because of that. Okay? Landau said, this is nonsense. You can't publish this paper. So it's only after Landau had his accident and then he died, this paper was published. But no, it's a true story. Landau did this for many people. Somebody came to him and said, sir, you can observe 21 centimeter radiation from the hyperfine levels of a hydrogen atom. This is nonsense. Every graduate student knows that this radiation cannot occur. So many times Landau made such a mistake. And so did Pauli. So did Einstein. Okay? Anyway, in 2003, Abrikosov shared the Nobel Prize with Ginsburg. Both cases 50 years late, but anyway, like in the case of Chandrasekhar, better late than never. Now, an important prediction of this theory of type II superconductor due to Abrikosov is that a superconductor can allow a magnetic field to go through it, provided it is in the form of quantized flux tubes, each with a quantum of flux hc divided by 2e. That is the quantum of flux, quantum of magnetic flux. Therefore, this is what happens. Outside the superconductor, the magnetic field is homogeneous both ways, but inside the magnetic field is confined to these quantized flux tubes. Now, this was a prediction made a very long time ago, 1958, by Abrikosov. Today, this is what you see experimentally. Here is a type II superconductor. These are the quantized flux tubes. Here is the number of quantized flux tubes as a function of the applied magnetic field. 1 Tesla, 2 Tesla, 3 Tesla, 5 Tesla. And here are the detailed crystal structure analysis. And there's a big industry of people creating these Abrikosov vortices and studying phase transitions in them. In other words, they become like a material for phase transition. So what you're doing is phase transition of this lattice of flux tube, how they melt, how they become a glass, how they become different kinds of crystal structures. It's like liquid crystal going from isotropic liquid to pneumatic liquid crystal to smectic liquid crystal to cholestic liquid crystal. Similar things are being now studied. So these are all experimental results. Okay. Now, proton superconductivity in neutron stars. So what one believes is that when neutron star cools, the protons will become superconducting. Therefore, inside the neutron star, the flux is in the form of Abrikosov vortices. And of course, when you look at a neutron star from outside, it will look like a dipole field for you. And we will return to this in this Friday's lecture when we discuss millisecond pulsars. So what you have inside a neutron star are two brands of spaghettis. One, the yellow ones, parallel to the rotation axis omega, are the Onsager-Feynman vortices in the neutron superfluid. And what you have parallel to the magnetic axis are the Abrikosov quantized flux vortices. And as I will discuss on Friday, these two brands of spaghettis stick to one another very strongly, and there are many astrophysical consequences of these things, such as star quakes, flux expulsion from the interior, plate tectonics in neutron stars, and so on. Some of these things were done by me first time, so I will discuss them on Friday. So let us summarize. our structure of a neutron star, the outermost layers of the solid crust or iron 56 lattice. As you go down, iron 56 is no longer the most stable nuclei, but then you can calculate what is the stable nucleus taking into account inverse beta decay. And then when you go above a density of 4.3 times 10 to the power 11 grams per cubic centimeter, you find a lattice of neutron-rich nuclei with a Fermi liquid of blue neutrons, which is shown in blue. And the point is that because the neutron star is rotating, this superfluid will have Feynman vortices in them. And then as you go inside the nuclear density, where you have the neutron-proton fluid, the neutrons will be superfluid, the protons will be superconducting, and the electrons will be normal. And both the superfluid and superconductor will be in a vortex state. There will be the Onsager-Feynman vortices in the neutron superfluid and the Abrikosov flux vortices. This is the only instance that I know of the coexistence of superfluidity and superconductivity with strong interaction between superconductivity and superfluidity. On Earth, we have superfluid, we have superconductor, we don't have coexistence of the two. So this was a very unique laboratory to study this, and it has very important consequences for millisecond pulsars, as we will discuss on Friday. So that is the journey to the center of a neutron star, and on Friday we will discuss millisecond pulsars. Are there questions in today? Yes?
Yeah, so like you said that due to quantum vortices, there should be star quakes in the neutron stars, right? But what will be their observational signatures that star quakes are happening in neutron stars, which you can pick up as signals?
Very simple. Very simple and straightforward. They're called star quakes. So, angular velocity of rotation of a neutron star as a function of time, you would expect the neutron star to slow down. So what you find every now and then is there is a sudden spinning up and then a very slow recovery. These are interpreted as the quakes. Okay? So suddenly there is it is almost as though the moment of inertia has changed, and therefore to conserve angular momentum, the angular velocity has changed. And this is seen in a lot of pulsars. It was first seen in pulsar which is 10,000 years old, called the Vela pulsar. This was first seen by Radhakrishnan, same person who did the 21 centimeter survey and so on. But it is now seen in a lot of pulsars. A pulsar like the crab is showing, sometimes it's spectacular like this, sometimes it is like a noise all the time. Now the question is, first people thought, I remember when this was first discovered, first people thought it was like a real earthquake. What they thought was, here is a neutron star, which is slowing down because it's emitting energy and angular momentum. Therefore, its shape must change. From a perfect sphere, it must become more and more oblate. But it cannot become oblate because the crust has such strong elastic properties that it cannot change from a spherical surface to an oblate surface. So what does it do? It builds up tremendous amounts of strain, till finally it exceeds the Hooke's law limit, and suddenly the crust yields. That was the mechanism people thought originally. It was actually called as star quakes. But then people realized that this could not be so, because this Vela pulsar glitched again within a year. Now, if you ask how much elastic stress could it have built up in 1 year, it is not enough to make the crust crack again. So they had to abandon the classical quake model right then and there. And then this very long recovery period, lasting 1 year, 2 years, and so on, convinced people that somehow the superfluid nature of the core must come in. And then P.W. Anderson and constructed the theory. I remember this, I was in the Cavendish at the time, he was also in the Cavendish when he did this work in terms of, because as the neutron star slows down, the number of Onsager-Feynman vortices has to decrease and they have to go out like this. Now suppose the vortices are not free to migrate, suppose they are pinned, suddenly they become unpinned. And so suddenly they deposit angular momentum and they come to the crust. So there's a lot of very serious physicists have worked on this, most notably P.W. Anderson. So that's the argument that what was believed to be a straightforward quake really has to do with the superfluid. See, the point I'm making is the following. The bucket is slowing down because it's emitting energy and angular momentum. The superfluid also must slow down. Does it slow down instantaneously? It cannot slow down instantaneously. It must annihilate the vortices. They migrate and they have to annihilate. Now, if that process is a slow, if there is a time constant connected with that process, that will be the time constant that you're talking about. Okay, so the arguments are very, very compelling. There's almost, you can argue whether it's the details, you can argue. But can you get away without invoking superfluid? I am convinced, I've thought about this for 30 years. There's no way you can construct any classical time scale of that length without invoking superfluid. A lot of people at Bain and others have come to the same conclusion.
This rotation is, this slowing down is happening continuously, right? So why it is like this releasing of vortices is a sudden process? It should also happen in a continuous manner.
I'm saying, let's say this is a beaker of superfluid, which is rotating, vortices are there. As I slow down the beaker, you're saying vortices should just move out. But you see, one of the peculiar things about vortices, dislocations, and things like that in solids is they pin. For example, the vortices can pin to the bottom of the beaker. Okay? This is well known. Vortices pin. See, this is one of the biggest problems in making superconducting magnets. Because as you increase the magnetic field, you're creating more and more of Abrikosov fluxes, okay? So it's a very serious problem people are worrying about. Pinning of vortices of any kind, whether it's a superfluid vortex or a superconducting vortex, to defects. Okay, so let us say the vortices pin to the bottom of the beaker. There will be a pinning energy associated with it. So if it doesn't unpin, there's going to be a strain on it, very similar to V cross V force. In the case of superfluid, that's called a Magnus force. I mean, a vortex, you're trying to drag it, but it's not able to drag because it is pinned, and there is a superfluid flowing past that vortex. It will experience a force very similar to V cross V force. Okay? So when that V cross B force exceeds the pinning force, pop, it will pop out. So the idea is that this pinning of, now if these two spaghettis are intertwined, like I claimed many years ago, almost 30 years ago now, 20, I don't remember, 30 years ago, yeah, 1990, almost 30 years ago, very strong pinning energy, like the guts in a tennis racket. And they're not interpinned just at one point. One of these spaghettis is interpinned at 10 to the power 20 points. So if one is there, so moving out of these vortices is a horrendous process. Okay? So there will be discontinuous phenomena associated with it, noise associated with it. By the way, if you look at the period of rotation of the Earth, which we call as the length of the day, it changes continuously. Okay? It changes continuously because there are earthquakes taking place in the earth all the time. Thousands and thousands of earthquakes are taking place this instant. I remember 8 years ago, I was in the Smithsonian Museum in Washington, and there in a room, there is a big map of the world unfolded like this, like in atlases. And there are LEDs lighting up. Bright LEDs, not so bright LEDs. Those are actual earthquakes. The data is transmitted live to Smithsonian from all over the world. So the earthquakes taking place all the time. Therefore, the moment of inertia of the earth is changing all the time. And therefore, omega is changing. And then you have a big storm in the Pacific Ocean, crossing the Andes mountain in South America. And that shifts the whole mountain range. You say, this is nonsense. This is not nonsense because you can measure this with radio telescopes. You have a radio telescope with triangulation, you can actually measure how much these plates shift. They shift enough to change the moment of inertia so significantly. So the length of the day is a very stochastic thing. Same thing with something like the Crab pulsar. Its period of rotation is changing all the time. There is very noisy behavior. And one of the explanations that P.W. Anderson gave for this after many years of very, very serious thinking is that this is connected to vortices, unpinning and things like that. Okay? As I will discuss on Friday, millisecond pulsars don't have any of these things. That's why they're so important in gravitational wave context today. Okay? And because they're so old, all these things have taken place in them. Yes.
So when you showed that the superfluid in a rotating vessel will mimic the rigid body rotation, so there was this graph of V versus R and that was linear. But for superfluids, like which is the velocity you are talking about? There are quantum vortices of circulation. So what is the?
See, all these vectors will add up. Because at any given radius, there are so many vortices. Next radius, you have to add them up vectorially. That was that curve. If you go to the center of each vortex, the velocity field will diverge. That's the meaning of vortex, isn't it? So microscopically, the velocity field will go to infinity, but macroscopically, it is a smooth behavior. So, okay. So the correct phrase I would like to make is a superfluid in a rotating bucket will mimic rigid body rotation. It is not rotating like a rigid body. Yeah. Read about this in Feynman's volume 3, Feynman lectures. I think there is a discussion of that. It's certainly one of his very beautiful pieces of work. Yes. Any other? Yes?
Classically, when you have a superconducting ring, say, if we subject it to a magnetic field, it expels the field from inside it. But if the magnetic field was already there and the metal was cooled, then the magnetic field is not expelled, but rather the flux of superconductor now becomes.
If the magnetic field is between two critical values, if the magnetic field is below a lower critical value, it will expel it. If the magnetic field is very strong, it destroys superconductivity.
But classically, that's not what happens.
No, that's what happens in laboratory. Type 2 superconductor, that's exactly what happens. Type 2 superconductor, see, type 1 superconductors has only one critical field. Below the critical field, the superconductor is a diamagnet. Above the critical field, the field destroys superconductivity. But in a type 2 superconductor, there are two critical fields. Between these two critical fields, you have this Abrikosov vortices. Yeah, those are the type 2. All alloys are type 2 superconductors.
I was just saying that because I have not studied about superconductivity, but the few problems that we have encountered about superconductivity, there we usually assume that the flux of the superconductor remains constant, not that the magnetic field becomes zero. So only if it was formed at zero magnetic field, then it expels all magnetic fields. Otherwise, it actually develops a net flux which remains constant.
No. That is true only if the field is between two critical values. go back and look at Kittel or some book in solid state physics. Anything else? Okay, so we'll meet on Friday and discuss millisecond pulsars.